In 2013, I figured out something that Einstein missed. Albert Einstein discovered general relativity, the theory of gravity and curved spacetime. He also helped discover quantum mechanics, the theory of the very small. But he died thinking these two theories were fundamentally incompatible. What I realized sitting on a beach in Northern California is that they're now separate. They're two descriptions of the same thing. Wormholes in quantum entanglement, ER and EPR, they're the SAM phenomenon. Let me tell you how Juan Maldacena and I figured this out. It's 2012. I'm on sabbatical and I'm in trouble. Four physicists, Almeri, Marolf, Polchinski, and Sully, we call them AMPS, just published a paper that threatens to destroy everything I've built over the past 20 years. They're saying that black hole horizons must be firewalls, walls of infinite energy that incinerate anything that crosses them. If they're right, my black hole complementarity principle, the thing I fought Stephen Hawking over for decades, is dead, wrong, a mistake. Joe Polchinski is a friend of mine, brilliant physicist. We've known each other for years, and he's just published a paper saying I'm wrong about black holes. The entire physics community is watching to see what I'll do. I'm walking on a beach in Northern California, thinking about this problem, and I'm stuck. The AMPS argument is airtight, mathematically perfect. They're saying that if you want to preserve quantum mechanics, if you want information to not be destroyed, then old black holes must have firewalls. The horizon can't be smooth. It has to be violent, and I'm thinking this can't be right. I've spent 30 years arguing that information isn't destroyed, that quantum mechanics survives. And now the price for saving quantum mechanics is that we have to give up everything we know about general relativity. That horizons are violent instead of smooth. That's insane. I'm walking along the beach, and suddenly I remember two papers, both from Einstein. The first paper, Einstein and Rosen, describes wormholes, bridges between two black holes. They called them Einstein-Rosen bridges, ER bridges. The second paper, Einstein, Podolsky, and Rosen, describes quantum entanglement. Two particles are mysteriously connected no matter how far apart they are. They called it EPR, same year, same authors, two completely different phenomena. And standing on that beach, I had this crazy thought, what if they're now different? What if ER equals EPR? What if every pair of entangled particles is connected by a wormhole? I called Juan Maldacena immediately. Juan's at the Institute for Advanced Study in Princeton, probably the smartest person I know. I said, Juan, I think I've figured it out. ER equals EPR, wormholes, ARE, entanglement. There was a long pause. Then he said, holy shit, Lenny, write it up. Let me back up and explain what we were dealing with. The firewall problem starts with a simple question: what happens to information that falls into a black hole? Stephen Hawking said in the 1970s that black holes evaporate. They emit radiation, Hawking radiation, and slowly shrink until they disappear completely. The problem is, Hawking's calculation said the radiation is completely random, thermal. It contains no information about what fell in. That means if you throw a book into a black hole, the information in that book, every word, every letter, is destroyed when the black hole evaporates. Gone forever. I spent 28 years fighting Stephen on this. I said, no, that violates quantum mechanics. Information can't be destroyed. It has to come out somehow in the Hawking radiation. In 2004, Stephen conceded. He agreed that information isn't destroyed. The physics community accepted that I was right, information must be preserved. But here's the problem, Acho Dau, how does the information get out? That's where AMPS comes in. They said, okay, Lenny, you're right that information isn't destroyed. But if information is preserved, then old black holes that have been evaporating for a long time, must have firewalls at their horizons. Here's why. Let's say you have two entangled particles. I'll call them Alice and Bob. They're created together, perfectly correlated. If Alice is measured spin up, Bob is guaranteed to be spin down. That's entanglement. Now let's say Bob falls into a black hole 50 years ago. The black hole has been evaporating ever since, emitting Hawking radiation. For the information to be preserved, for my complementarity principle to work, that early Hawking radiation has to be entangled with whatever fell in. That means the radiation is entangled with Bob, but Alice is also entangled with Bob. And here's the problem in quantum mechanics. A particle can only be maximally entangled with any other system at a time. You can't have Bob entangled with both Alice and the Hawking radiation. That's called the monogamy of entanglement. So something has to break. Either Bob stops being entangled with Alice, or he stops being entangled with the radiation. AMPS said if Bob stops being entangled with Alice when he crosses the horizon, that violates the equivalence principle. The equivalence principle says that an observer falling into a black hole shouldn't notice anything special at the horizon. It should be smooth, but breaking entanglement requires energy, a lot of energy. That's the firewall. Their conclusion, if you want quantum mechanics to work, if you want information to be preserved, then black hole horizons must be violent. Firewalls are unavoidable. I read that paper and thought there has to be another way. We can't give up the equivalence principle. General relativity works. We've tested it 1,000,000 times. Horizons are smooth in Einstein's theory. But I couldn't see the way out. That's when I had this crazy idea about ER and EPR. Let me explain what these are, because this is the key to everything. ER, Einstein-Rosen bridges, are wormholes. In 1935, Einstein and Nathan Rosen showed that general relativity allows these structures. You have two black holes far apart in space, but they're connected by a tunnel, a bridge through space-time. If you could somehow travel through the bridge, you'd go from one black hole to the other faster than light could travel the long way around. Now, these Einstein-Rosen bridges are non-traversable. You can't actually travel through them. The throat of the wormhole pinches off before you can get through. But mathematically they exist. Two black holes connected by a wormhole. EPR, Einstein, Podolsky, Rosen, is quantum entanglement. 35. Einstein, Podolsky, and Rosen showed that quantum mechanics predicts these weird correlations between particles. You measure one particle, and instantly, faster than light, the other particle's state is determined no matter how far apart they are. Einstein hated this. He called it spooky action at a distance. He thought it proved quantum mechanics was incomplete. There must be hidden variables, he said, some deeper theory underneath. But experiments proved Einstein wrong. Entanglement is real. It's one of the most well-tested predictions in all of physics. So here's what I realized on that beach. What if these two things, wormholes and entanglement, are the same? Think about it. Both involve two systems that are mysteriously connected. With wormholes, two black holes are connected through space-time. With entanglement, two particles are connected through what? Through nothing, apparently. Just this abstract quantum correlation. But what if the connection isn't abstract? What if entanglement creates geometry? What if every pair of entangled particles is connected by a tiny wormhole? ER equals EPR, Einstein-Rosen bridges are Einstein-Podolsky, Rosen entanglement. Now, I know what you're thinking. This sounds crazy. How can entanglement, this purely quantum thing, create geometry? How can two particles be connected by a wormhole? Let me give you an analogy. Think of space-time like a fabric. That's the usual analogy, and it works here. Normally, two distant points in space are separate, they're not connected. But if you entangle two particles at those 2 points, you create a thread connecting them. A tiny wormhole. The fabric of space-time develops a connection that wasn't there before. The more entanglement you have, the stronger the connection. With just a few particle pairs, the wormhole is microscopic. Quantum scale. You could never travel through it, but with a huge amount of entanglement, the kind you get with two entangled black holes, you get a macroscopic wormhole, an Einstein-Rosen bridge. Juan and I worked out the details. We showed that if you have two black holes that are maximally entangled, perfectly correlated quantum mechanically, then general relativity says they must be connected by a wormhole. The geometry and the entanglement go hand in hand. Here's the beautiful part. This solves the firewall problem. Remember the AMPS argument? Bob falls into a black hole. He's entangled with Alice outside, but he's also entangled with the early Hawking radiation. Monogamy of entanglement says he can't be entangled with both. So something breaks and you get a firewall, but EPR says that's not how it works. Bob isn't just entangled with Alice through some abstract quantum correlation. He's connected to Alice by a wormhole, and when Bob falls into the black hole, he's also connected to the Hawking radiation by wormholes. These are geometric connections, different wormholes. No monogamy problem. The horizon is smooth, no firewall. Bob falls through without noticing anything special, just like Einstein's equivalence principle predicts. But quantum mechanics is preserved too. The information isn't destroyed, it's encoded in the geometry of all these wormholes connecting the black hole interior to the Hawking radiation. Juan and I published this in 2013. The paper is called Cool Horizons for Entangled Black Holes. The title is a joke. The opposite of firewalls is cool horizons. The horizons are smooth and cool, not violent and hot. The response from the physics community was mixed. Some people got it immediately. They saw that this was a way to unify quantum mechanics and general relativity at a conceptual level. Entanglement isn't just this abstract quantum thing, it's geometric. It creates space-time connections. But a lot of people were skeptical. And I get it. This is a radical idea. You're saying that every pair of entangled particles everywhere in the universe is connected by a wormhole. Even the electrons in your body, if they're entangled with anything, have tiny wormholes connecting them. That's BRD. Joe Polchinski, one of the AMPS authors, was cautious. He said, okay, maybe ER-EPR solves part of the firewall problem, but there are still issues. What about computational complexity? What about the interior geometry? We had long discussions about this. Joe was brilliant, and he pushed us to think harder, Juan, and I kept working on it. We showed that ER-EPR isn't just about black holes. It applies to ANY, entangled system. Two particles entangled in a lab on Earth. They're connected by a microscopic wormhole. You'd never notice it. It's far too small to measure. But it's there according to our proposal. This idea has now become a major research direction. People are exploring what it means for quantum information theory, for quantum computing, for our understanding of spacetime itself. Some physicists have built on this to argue that spacetime emerges from entanglement. That at the most fundamental level, space doesn't exist. Only quantum information exists. And when you have entanglement, you get geometry, you get spacetime. Yeah. It's entanglement all the way down. Mark van Ramsdonk at the University of British Columbia has done beautiful work on this. He showed that in the ADIS-CFT correspondence, this connection between gravity and quantum field theory that Juan Maldacena discovered, entanglement in the quantum field theory corresponds to connectivity in spacetime. Cut the entanglement, and space-time falls apart. Space is held together by quantum correlations. That's the power of ER-EPR. It's not just a solution to the firewall problem. It's a whole new way of thinking about the relationship between quantum mechanics and gravity. Of course, not everyone is convinced. Some people still think firewalls might be real under certain conditions. The debate continues. That's how physics works. You propose an idea, other people test it, push it, try to break it. The ideas that survive get stronger, but here's what I'm confident about: entanglement and geometry are connected. Quantum mechanics and general relativity aren't separate theories describing separate aspects of reality. They're two descriptions of the same underlying structure. ER-EPR captures that connection. This work connects to almost everything I've done in the last 20 years. It ties back to the holographic principle. Remember, holography says that everything inside a volume of space can be described by information on the boundary. Why? Because of entanglement. The interior and the boundary are entangled, and that entanglement creates a geometric connection between them. ER-EPR explains HOW holography works. It connects to my work on black hole complementarity. Complementarity says that an observer falling into a black hole and an observer staying outside can both have valid descriptions, even if they seem contradictory. ER-EPR shows why the two observers are connected by wormholes to different systems. They're measuring different aspects of the same quantum state. It connects to quantum complexity, the research I've been doing with Adam, Brown, and others. If entanglement creates geometry, then as a quantum state becomes more complex, the geometry it creates becomes more intricate. The wormhole connecting two black holes grows longer as the quantum state inside becomes more scrambled. Complexity and geometry are linked, and it connects to the biggest question I'm working on now, de Sitter holography. Our universe is accelerating. It's a de Sitter space with a cosmological horizon. How do you do holography in de Sitter? How do you describe entanglement when every observer has a different horizon? ER-EPR might be the key. If horizons are created by entanglement, then understanding entanglement in de Sitter space is the path to understanding the holography of our actual universe. Juan and I are still working on extensions of this idea. So are dozens of other physicists around the world. This is a living research program. You know what strikes me about ER-EPR? It's that Einstein was always close. In 1935, he wrote two papers, one about wormholes, one about entanglement. He saw these as two separate things. He thought entanglement was a problem with quantum mechanics, that it proved the theory was incomplete. But he was wrong about that. Entanglement is real. It's fundamental. And what Juan and I showed is that Einstein's two 1935 discoveries aren't separate at all. They're the same thing. He just didn't realize it. If Einstein had lived another 20 years, if he'd seen how quantum mechanics and general relativity developed, I wonder if he would have figured out EPR himself. He had all the pieces. He just didn't put them together. That's the beauty of physics. Sometimes the answer is hiding in plain sight. Two papers, same year, same authors. Took us 78 years to realize they were describing the same phenomenon. After 50 years of doing physics, this is what I've learned: the universe is connected in ways we're only beginning to understand. Particles separated by billions of light years, connected by microscopic wormholes. Space itself, held together by quantum entanglement. Every time I think I understand how strange reality is, it gets stranger, and I love it. Next, I want to talk about what happens when you don't have entanglement, when space-time falls apart. That's the story of my work on complexity and the Python's lunch. But that's for another time.